Okay, so you've got a new homework assignment that'll be due on Thursday of this week. So that's a quick turnaround. Today is your first introduction to Chapter 14, first and only. We're going to cover the entire chapter in one lecture. And then your assignment is due on Thursday. The good news is that the entire chapter basically hinges on one concept, and it's not rocket science, as they say, not brain surgery. All right. So one hint is that on problem 25, you should assume that the coefficient of contraction is 0.6. Anybody remember what C sub C means? What is that coefficient of contraction? Maybe I'll draw a visual clue. It involves a gate. So we've got water behind the gate. What's the C sub C?
Kind of ratio.
It's a ratio, oh yeah. Right. So the water comes out of the gate, it contracts a little bit. I didn't draw the channel bed very horizontal. Let me do a better job about that. All right, now the channel bed is horizontal. So here is the gate height W, and then here is the water depth after it has contracted. So we would call this, like if we're referring to the gate, Y2, and then this is Y1. It depends on what kind of a problem you've got. Is this a hydraulic jump problem or a gate problem? So I'm calling this 1 and this 2 because it's a gate problem as I'm looking at it right now. So C sub C is the ratio Y2 divided by W. So it's saying after the water depth contracts, the depth is 60% of what the gate height opening was. It doesn't give you that C sub C value in the problem data. Well, let's just all be on the same page and assume that. Okay. So that'll be due on Thursday. So let's get into it. Gradually varying flow is what is happening most of the time. Hydraulic jump day is a special day because rapidly varying flow is kind of a rare thing. You don't see it everywhere. You can see it sometimes in nature, but gradually varied flow is the dominating type of flow that you have in most open channels. It's pretty uncommon for us to have steady uniform flow. So you don't see the normal depth all that often unless it's a really long stretch of prismatic, man-made, engineered channel. Then you might see the normal depth. But if you think about a stream running along the side of the road or a river, most of the time the flow will be gradually varying. There will be variations in the depth, the width, the velocity, the slope. Something's changing somewhere, and so chances are is that the flow depth and flow conditions are reacting to that. So there's lots of different engineered structures that can cause gradually varying flow, and there are lots of natural objects that occur inside of flow that can also induce this gradual variation. So a few notes. When the depth changes, so does the average velocity, assuming that the flow rate is the same. So let's say that conditions are steady, meaning that they're not changing over time. So the flow rate into some channel section and the flow rate out of the channel section are the same. But the velocity is still changing because the channel cross-section changes. So the velocity isn't the same into a variation as it is out. Just for purposes of simplicity, we'll assume that hydrostatic conditions apply, and that just means that as you go down through the fluid, the pressure increases according to the rate delta P is gamma times delta H, where delta H is some distance down into the fluid. Now, that's the hydrostatic equation, static, with the emphasis on static. That presumes that the water isn't moving. But in most channels, the water is moving slowly enough that the hydrostatic equation is a good approximation for what the actual pressure is at some depth. We are going to account for energy loss. We didn't account for energy loss not directly when we were doing rapidly varying flow. Remember that when we had a hydraulic jump, here's the flow when it's supercritical and it jumps up to the subcritical depth. We did have a delta E that we calculated, but that delta E was just accounting for the energy loss due to turbulence, really. It wasn't accounting for the friction loss of the channel pushing against the flow as the water is going downstream. So we are going to have to account for that energy loss because in rapidly varying flow, location 1 and location 2 were pretty close together. The jump that we saw back in the lab was only about 40 centimeters long. So the upstream and the downstream really don't experience very much resistance due to the channel. But in gradually varying flow, where you've got a channel that has depth changing very slowly, it might be that location 1 and location 2 are several kilometers apart. And so we can't ignore frictional losses over that extended length. So the process we go through is going to account for energy loss. So let's just begin by looking at some sorts of structures and flow conditions that could cause gradually varying flow. And we've looked at diagrams similar to this before. What we were looking at is we were looking at what causes a hydraulic jump. So this is similar. We want to look at what sort of thing causes gradually varying flow. And so here we've got a gate that is choking the flow. The gate is opened so little that the water depth had to pool upstream so that there could accumulate enough energy to get a huge, big velocity underneath that gate. And so the section that is GVF is just where it is going from the normal depth up until the gate face. Any guess on what UF means? Right, uniform flow. And again, what is uniform flow? It's the same depth everywhere. It's going to be the normal depth here, and if you go upstream a little bit, it'll be normal depth. It's just that section of the stream that is unaffected by the pooling. The pooling doesn't continue infinitely upstream. There is a finite length that pooling will accumulate. So that's one potential cause of gradually varying flow. Here's another. You can see that there's a section where the water depth is decreasing as the flow approaches a drop-off. Here's another. I've shown you this figure before where we had two different slopes. And what you can see here is that the second slope is more mild than the first one, meaning it has a shallower slope. And so the depth is bigger, the normal depth is larger. And so joining the upstream normal depth and the downstream normal depth, there has to be some gradual transition linking them. And in both of these cases, both of the slopes are either steep or both of the slopes are mild. And we could see this transition as long as they're both steep or both mild. But if this one was steep and then this one was mild, then we'd have to see a hydraulic jump. So in that case, they're both the same critical designation. Here's another one. Gradually varying flow, and then it goes to uniform flow. So what do we know about the slope in this lower right-hand diagram? If we don't see a hydraulic jump, what does that tell us about the slope? It's steep. The other way to say it is, and this is, the text puts it, that this slope cannot support a hydraulic jump. So we have supercritical flow coming out from underneath the gate, and it stays supercritical because the slope is so steep. And so we've gone back to the normal depth without a hydraulic jump in between. And so this happens to be a steep slope. So any questions so far on the concepts behind uniform flow? All right. So what we're going to do is try and develop a series of equations that we can use to predict the depth. I mean, that's where we're headed. Long-term view is I want to be able to say, well, if my gate is open this much here, what's the depth 5 meters downstream? Or what's the depth 6 meters downstream? I want to be able to characterize the shape of the water surface so I can always predict how deep the water will be. And it's not just for this diagram, for all of them. If I have water approaching a drop-off, I want to be able to say, all right, I know the normal depth is here, and I've got gradually varying flow, and so what will be the water depth 25 meters downstream of where I knew the normal depth? Basically, what we'll be doing is picking a spot where we know the depth and then trying to estimate it some distance either upstream or downstream. So that's what we're trying to develop, is the ability to predict depth. And as we do that, these are the assumptions that we're going to make. Let's work with prismatic channels, and if you remember back what that means, is it means a regular cross-section. A prismatic channel is one that's trapezoidal or rectangular. This would not be a prismatic channel. And so if we have a non-prismatic channel, we have to try and approximate it with the series of prismatic shapes. We're going to assume steady flow, meaning that conditions aren't changing over time. Relatively small bed slopes, and that's a pretty good assumption because any slope that's less than 5% is going to be representative of most of the streams out there. Uniform velocity distribution. And that gave us problems when we were working with hydraulic jumps. Remember, that was the assumption that we said was probably not super accurate in a hydraulic jump, because the uniform velocity distribution, when we had supercritical flow, it was saying that the depth of the velocity right under the surface was the same as the velocity right up against the bottom of the channel. And so it made it easy to do our calculations, but it introduced a little bit of error. Here, in gradually varying flow, it's not as egregious for us because the depths are bigger than they are in hydraulic jumps, and the water's moving more slowly, and so there's not as big a difference in the velocity submerged as there is at the velocity at the surface. Kinetic energy correction factor has to do with whether the velocity distribution is parabolic or not. And since we won't have laminar conditions in nature almost ever, then a kinetic energy correction factor of 1 is fine. Parallel streamlines, channel roughness is constant. Just things to be aware of as we go through this process equation that we're going to look at. So here is a diagram that represents the water depth getting larger downstream. And there's 3 important slopes we have to continue to be aware of. Remember that there is the S sub f, which is the slope of the energy grade line, and here they're abbreviating it TEL, which means total energy line. So total energy line is the same as energy grade line. It's just a difference in terminology between your fluid mechanics book and the hydraulics book. It means the same thing. That dashed line that's hovering above the water surface, that's the energy grade line. So S sub f describes the slope of the energy grade line. S sub w describes the slope of the water surface. And then finally there's S naught, which is the slope of the channel bed. So those are the 3 slopes that we're going to be keeping track of in the process equation. And today, what I'm going to try and, the equation that we're looking at tells us how is the water surface slope changing relative to the bed. And so is the water getting deeper or shallower depends on whether or not S naught and SW are parallel. So let's say S naught and SW are parallel. So S naught is equal to SW. So is the water getting deeper or shallower? Neither. That was a trick question, wasn't it? You smoked that one. All right, so there's no change in depth. Okay? What if we have, here is our S naught, and here is our SW. And so SW is bigger than S naught, more negative. So it's obviously it's getting shallower, right? And then here we've got a steep S naught. So we want this one to be S naught is bigger than SW. So that's steep. And this isn't very steep. And so you can see that now the water's getting deeper. So the equation we're developing today, it doesn't predict S naught. That's usually in the problem description. It doesn't directly predict SW. What it's predicting is the difference between S naught and SW. Okay? So let's look at what this diagram is showing us. We've got location 1 upstream, location 2 downstream. Water is flowing at some velocity. We've got some depth, y. The velocity head is above that, depending on whatever the velocity was. So then the water is flowing downhill, and you can see that there's S naught is the slope. And the way that we know the change in elevation, you see S naught times dl, where dl is the distance between 1 and 2. That's the delta z from 1 to 2. So at location 2, the water depth is different, and so is the velocity. You know, the water depth is bigger than it used to be. This blue line represents the depth at 1, and then it also got a little bit deeper. So what does that tell us about the velocity? If it got deeper, then the velocity must have slowed down. And so here it says v plus dv. Well, the dv must be negative if it slowed down. Okay, so that the change in velocity was a decrease. Since the change in velocity was a decrease, then the velocity head also decreases. And so that's why over here at 1, this dashed line was higher above the water surface, is because if you've got more velocity, then the energy grade line is higher above the water surface than down here at 2, where the water velocity is lower, and so there's less of a deflection. Okay, so does everybody feel like they understand the diagram here? It doesn't show us what's causing this. We don't know yet why it's getting deeper downstream, but we can tell just by looking that it's getting deeper downstream. Maybe there's some sort of a choke. You know, it doesn't matter, really, as for the purposes of this diagram, what's causing it. So where the process equation comes from that we're going to have and use today is it starts with the definition of specific energy, where specific energy, E, is the sum of the depth plus the velocity head. And here, just for purposes of simplicity, we can express the velocity head in terms of Q rather than in terms of V. And so if we take the derivative of that with respect to y, then we've got dE dy is 1 minus the Froude number squared. We've seen that before. And so let's make a couple of substitutions here. The definition of S sub f, where S sub f is the slope of the energy grade line, they're calling that dH/dl, and H is the total head, including the specific energy and the elevation. And so E is only depth and velocity head, but H is depth, velocity head, and whatever elevation above the datum we've got, the z. And so here at 1, we've got some z. It's the S naught times dl. So let's substitute this for dH/dl and substitute the slope of the channel bed for dz/dl. So when we do that, this is what we end up with, and this is called the process equation. That's what the book calls it anyway. I always think that's kind of a funny name, you know, like the process. It seems funny to me. I don't know. But anyways, this is the governing equation for gradually varying flow. So does anybody remember what I said we want to be able to do with gradually varying flow? Like, what's our ultimate objective? We want to be able to predict the depths as they're changing. And so in gradually varying flow, we have depth increasing or decreasing. Let me just draw a little diagram here to make an important point about the limit of the process equation. Okay, so let's say that water is flowing off the edge of a cliff. Okay? Here's y1. We know, maybe we just know that here the depth is 3 meters. This process equation here says the change in depth with respect to some length, where here's the dl. So let's say that I'm interested in knowing 10 meters downstream from here. What if I wanted to know what's the depth there? Okay, so this process equation says I can tell you the change in depth with respect to some distance apart. But the rub is that this implementation of it only tells you the relative difference between the channel bed slope and the slope of the energy grade line at a point. And so if I applied this process equation here at 1, it's going to tell me how does the water surface slope, or really, actually, the energy grade line slope, how does that compare to the slope of the bed, S naught? So here's S naught, here's S sub F. So what it does is it extends linearly, but we've got a curving water surface. And so all of the methods we're going to use that build on this process equation break up the distances into little small segments, because we want to be able to just approximate each of these steps as lines, because it's a curve and we can't just, to make it as obvious as I can, if we were trying to find the depth at 2 by applying the process equation, it would just do this. It would say, well, your depth is decreasing, so here's your depth. And what you can see is that it continues, it's a nonlinear trend. The depth is getting lower and lower at an increasing rate. And so this process equation is only valid at a point. That's why I've put that in bold. Actually, I think I just maybe bolded that today. Is it bold in your notes? Oh, it's already bold in your notes? All right. Well, maybe circle it anyways, because it's important. In the final exam, it never fails. Someone tries to use the process equation to predict a downstream depth, and it doesn't work, because it only tells you the slope of the water surface at a certain point. Not the change, because the water surface slope is changing. It's not constant. Here in the original diagram I drew, you can see that the slope is getting steeper and steeper and steeper. And so the slope is changing, but this only can be used to tell you the slope at the location where you apply it. Like you're going to say, right here at this spot that I'm interested in, I know the slope of the energy grade line there, and I know the Froude number there, and I know the channel bed slope, and so it'll tell you the water surface slope right here. But it doesn't tell you the water surface slope here, because at that location, at any other location, the Froude number is going to be different and the slope of the energy grade line is going to be different. Okay? So this is how you use the process equation to find the slope of the water surface. dy dl is basically taking into account the channel bed slope and the slope of the water surface. Now, here's an important point for the homework. S naught is usually negative, right? Because water usually flows downhill, unless you're like at an amusement park and you're one of those water roller coasters or something. So when it says that, you know, a river has a slope of 0.01, when you're substituting that into this equation, you need to say negative 0.01 for S naught. But dy dl, it can be positive or negative. And, you know, when you go through the calculations, maybe you'll get a positive value, maybe you'll get a negative value. And that makes sense, because it could be that the water is getting shallower, or it could be that the water is getting deeper. And so here's an example of dy dl is negative, and here's an example of when dy dl is positive. So just again, in the margin, write a note to yourself, dy dl can be positive or negative. S naught is always negative. Okay. And you'll have to remember that in the example we're going to work in just a minute. Okay, so there's some different ways to look at this equation. S sub f is the slope of the energy grade line, and a good way for us to know what that slope of the energy grade line is to use Manning's equation. Remember Manning's equation, where in SI units it's Q equals A to the 5/3, N value P to the 2/3, and then slope to the 1/2. That's Manning's equation in SI. What do we put in front of it if it's BG units? There's like a number, a prefix. Good, 1.49. Yeah, that's if it's BG units. Okay, so what they've done here is solve S sub f from the, substitute S sub f for both SI units and BG units. These come from Manning's equation. This v squared n squared divided by r to the 4/3. That is has its origin in Manning's equation. Both of these are true for any shape, whether it's a trapezoid or a circular channel or a triangular channel. When you make your equation sheet for the final exam, clearly differentiate between, this equation's always valid and this equation only used for a rectangular channel, right? Because you can get into trouble if you misuse the equations. In fact, this one, it's not only has to be rectangular, but it has to be a wide rectangular section. Actually, if it's a wide section, it doesn't matter if it's trapezoidal. But do you remember when we talked about wide before? How wide is wide? What's the criteria for how wide is wide? 20 times. Yeah, so here's our depth and here's our channel width. What we want to see for a channel to be wide is that B is more than 20y. I think I've written that right. Yeah. So if it's more than 20, equal to or greater than 20 times the depth, the width is, then you can use this. It doesn't look that much easier, but well, when a section is wide, what we're assuming is that it effectively is rectangular, because whatever shape it has on the edge is irrelevant. So I did start off to say it's rectangular, but then I remembered it doesn't matter. Okay, the other point I'll emphasize again is that this is only finding conditions at a certain point. It's only telling you what the slope of the water surface is. You use it to find the slope of the water surface, but only at a certain point, not over some range. It's not an average slope of the water surface. It's just here at this location where you've got whatever the normal depth is at that location, or whatever the flow depth is at that location, I should say. Okay, so again, this is called the process equation. Here's what it came from. Here is SI units. Here are BG units. Either of these are for any shape, and then this is only for a wide channel. And the sign of it tells you whether the water depth is getting deeper or shallower, as I showed on the whiteboard there. Just to continue our discussion of what is a wide channel, here's Manning's equation for a channel that's wide. So it's easier for us to find the normal depth. You can find the normal depth just by having the flow per unit width. That's what lowercase q is it's big Q divided by B. So the normal depth is a bit easier to find if the channel is wide. Okay, so here's our example, and I would like you to to take a crack at this one, and what you should do in your calculations is start off by finding the critical depth and the normal depth. And lo and behold, in the problem statement, we're given the information that leads us to believe the channel's wide. You'll notice that the width of the channel is 40 meters and the depth is 2. So it's just barely at the threshold of being wide, and that makes things a little bit easier for us in terms of calculating the critical depth and the normal depth and so on. Okay, so calculate y sub c, calculate y sub n using the formula from the previous page, and then calculate dy dl to try and find what the slope is. And so this is the rate of flow depth variation. When I ask you to find that, what I'm saying is calculate dy dl. All right, so I'm going to turn you loose on that, and then we'll talk about what you've calculated. The only place we consider S naught being negative is when we put it in here. You know, like this is still just Manning's equation, and so we won't put the negative value for the slope there or here, actually. It's not until this equation that we give it the negative value. Confusing, right? That's just the way that the sign convention is. If we used it negative everywhere, then we'd need to rearrange this expression as well. So let me tell you what we've got. We've calculated at some certain spot, we know that the flow depth, the water is at 2 meters here, where we're interested. This is our point of interest. Okay, so we calculated the critical depth, and the critical depth is 0.2943. So here's our critical depth. Y sub c is 0.29 meters. The normal depth was 0.912 meters. Have I got another color? All right. So here's our normal depth. So y sub n was 0.91. So here, the depth at the point of interest is larger than the normal depth, y sub n, and that's larger than the critical depth. So we already can understand some things about the flow situation by comparing the normal depth and the critical depth. If the normal depth is bigger than the critical depth, that tells you the conditions are mild, meaning that you have subcritical flow. You know, if you had steady, uniform flow on this slope, it would be subcritical. So since yn is bigger than yc, the slope is mild. And again, mild slope means conditions will be subcritical under uniform flow. But this isn't uniform flow. Here, from the sign of the dy dl, that's a positive sign, so that tells us that the water is getting deeper in the direction of flow. That's the interpretation of it. So what is the rate of flow depth variation? It is getting 1.39 times 10 to the minus 4th meters deeper for every meter of length in the direction of flow. So it's not getting deeper very fast. It's getting deep really, really slowly. But it is getting deeper in the direction of flow. The fact that the the depth is increasing or decreasing? It's increasing because that's not a negative number. Yeah. Okay, lastly, here's a phrase that I took directly from the homework. What is the water surface slope with respect to horizontal? Okay, so the water surface slope with respect to horizontal. What that tells us we need to do is compare dy dl. Here we've got dy dl is 1.39 times 10 to the minus fourth. And now this is where we have to say the slope of the channel is actually downhill. So negative 1.5 times 10 to the minus fourth. Before now, it's always been assumed that S naught is downhill, and so it wasn't built. That assumption was already built into the equation. But here, since dy dl could be positive or it could be negative, we have to be explicit about what the sign of S naught is, because dy dl could go either way. So now we have to say, well, no, S naught is a negative number. So the slope of the water surface, SW, is going to be S naught plus dy dl. And so that is negative 1.5 times 10 to the minus fourth plus 1.39 times 10 to the minus fourth, which means the slope of the water surface is going to be negative 1.1 times 10 to the minus fifth. So this is confusing, but if you stick with me for 30 seconds, you'll get up over the hump and you'll be like in enlightenment. All right? So over here, this meant the water is getting deeper. That's what a positive value for dy dl means. The water is getting deeper. And it's true, the water is getting deeper. So what does this mean? A negative SW. It's a negative sign. But over here, I just told you the water is getting deeper. How can the water be getting deeper, but the slope of the water surface be negative? How do we reconcile that? Exactly. The slope of the channel is more downhill. It's going downhill faster than the water itself is getting deeper. So relative to horizontal, the water surface is negative. But relative to the channel bottom, it's getting deeper. So if we were going to do a drawing of that, we had one earlier where basically we have, here's our channel, and the channel is steeper than the water surface, and so the water may be getting deeper, but if you compared, here's our horizontal datum. Okay, for this little sketch I'm doing here, what a mess. Okay, here's S naught, here's SW. So the water is getting deeper, but the water slope is still downhill. Okay? So that's how we reconcile those two seeming contradictions. Any questions from the example? All right. In the homework, it asks you to classify the water surface profiles. And in the last example we looked at, there were three depths. There was Y, the actual depth at a certain location. Here they're using that same phrase again, at a certain location. Because remember, the process equation only applies at a point. So there's Y, there's the normal depth, Y sub n, and the critical depth, Y sub c. And all three of those depths go into the process equation. Y sub n, Y, and YC. And those three depths are important not just because we use them to calculate dy dl, but also because they allow us to understand the water surface profile type. And I told you before that if you look at yn and yc, and yn is bigger than yc, then that tells you the slope is mild. Well, we can say the reverse of that. If yc is bigger than yn, then the slope is steep. Those three depths are going to be useful for classifying the gradually varying flow because they divide the stream up into three zones. Zone 1, no, wait, hold on. All right. It is 1, 2, and 3, I think. Did I get it the other way? Let's see. 1, 2, and 3. 1 at the top. It's been a year. All right. 1 at the top. 1, 2, and 3. Okay, so the water surface profiles, first of all, you classify it based on whether the slope is steep, mild, or the other less common options for the slope is that the conditions are critical, meaning that the slope just happens to be the same as whatever slope is required for critical flow, or a horizontal slope means that the channel is just going to be accumulating depth, or it could be an upstream, which is adverse. So there's M, S, C, H, and A. Just the first word happens to deal with classifying the slope, and you get that by comparing the normal depth and the critical depth. And so for these figures, you can see the mild is the one where the normal depth, y naught, is greater than the critical depth, yc. The steep is the reverse of that. Critical is when they're equal. In the horizontal slope, there is no normal depth. There's only a critical depth, and the same with adverse. Okay, so you first classify a profile with that letter, and then there is the number. So 1 at the top, 3 at the bottom, and the zones, basically, if the water at the certain location is in zone 1, then let's say the conditions were mild, then that would be an M1 profile. If you had a mild slope and the water depth, the flow depth is greater than both yn and y naught. The normal depth and the critical depth. That puts you into zone 1. Here you see it says y naught or yc. It's because this diagram could be true for either a steep slope or a mild slope. So let me break that up into the two possibilities. If the slope is steep, then that is when, for our certain channel, we're going to see the critical depth is bigger than the normal depth. And so here are the three zones, zone 1, zone 2, and zone 3. Okay, so that's if it's steep. And so here where it's on the screen saying y naught or yc, in the steep, it's the yc that's above the normal depth. And if it's mild, then that is when we have it the other way around, where we've got on top of it is the normal depth, and then beneath is the critical depth. And here's zone 1, zone 2, zone 3. Okay. So we're going to look at some pictures of different flow conditions, and they're going to have these M1, S3. They're going to have classifications, and it basically can just be found by where is the depth, the flow depth inside of one of those three zones, and then what is the slope. So there's zone 1, 2, and 3. One's above both of the lines, one's between the two, and one's below both of the lines. So if you look at the water surface is increasing, we know that that is because dy dl is positive. If it's decreasing, that's because dy dl is negative. If it's constant, that's from uniform flow. And there's a special case where you've got water going over the edge, negative infinity, or it could be during a flash flood where it's not steady conditions. So here's the M1, M2, and M3 profile. And what it shows you is that the water depth is always increasing for an M1 and an M3 profile. So look at the diagram shows you the water is getting deeper in an M1 profile, and it's M because the slope is less than the critical slope. So the critical slope is the dividing line between supercritical flow and subcritical flow. So we've got a very shallow, mild slope there. So that's where the M comes from. And depending on what are in the problem statement, it would tell you the depth, and you would compare the depth to Y0 and YC to see where in these three zones the water depth is. And just from this diagram, you'd know, even before calculating the process equation, you could use the diagram to predict whether the process equation should be negative or whether it should be positive. Here's the diagram for the steep slopes, and it shows you that it's positive for both zone 1 and zone 3 and decreasing for zone 2. So there are certain things that would cause these conditions, and we'll look at, first of all, these are the water surface profiles just in isolation, but then we'll look at the profiles in the context of those hydraulic structures and the change in channel configuration that could cause these shapes. Here's for the critical slope, horizontal, adverse. Really, it's steep and mild that I'm interested in you learning. The critical, horizontal, and adverse profiles are pretty uncommon. Okay, so here are those figures that show you what would cause an M1 profile. Okay, so M1, M means mild. It means the normal depth is greater than the critical depth. And in an M1 section, that means that the actual flow depth is even greater than both of those others. So the water depth is increasing, such as the water approaches some obstruction, like here it's showing a spillway. Okay, an M2 profile means that the water depth, it used to be a mild, it's mild, meaning that the normal depth is bigger than the critical depth, but now during the M2 section, the depth is getting lower. And so that would be flow over the edge of something. An M3 profile, it's a mild slope. That's why we're seeing a hydraulic jump. If it wasn't a mild slope, there wouldn't be a hydraulic jump. So it goes through the M3 transition until it has rapidly varying flow. Upstream of the gate is M1 because that is an obstruction that causes pooling. Okay? So here are three possibilities that could cause an S1 profile, an S2, and an S3. So in the case of an S1, you have the water depth increasing upstream of obstruction, but since it's a steep slope, that means that there has to be a hydraulic jump to go from the normal depth up to the sequent of the normal depth where the water depth is bigger than critical. The S2 profile, it's decreasing. The water depth is decreasing after a step up. And S3, the water depth is increasing after a gate. So in the homework assignment, it asks you to do a couple of sketches. I think actually on two of the problems you have to do drawings. And so they ask you, like, what kind of structure could be causing the profile. You'll do the numerical calculations and you'll get maybe that it's a mild profile. And so look at these drawings and you say, okay, I've got a mild slope. Is it an M1, an M2, or an M3? And you can know that by comparing the depth that they give you to the YC and the Y0. And so these are some of the hypothetical causes of an M1, an M2, and an M3. And it shows you the water depth increasing or decreasing, depending on what the case may be. And here's just from another text, the same thing is being summarized. That in a mild slope, what you have is the normal is greater than the critical, depth increasing, depth decreasing. So that's the sign of the dy dx, or we've been calling it dy dl till now. Okay, That is all for today. The assignment's due on Thursday. So I think with the example we worked and the pictures that we were just looking at, you should be able to solve that homework assignment. I will see you in class then.